Hello guys, welcome back to another tutorial. Hit the bell icon button so that you don't miss out any tutorial.
I'd like to welcome you all to this course on Webpack sponsored by EduOnix. My name is Matthew Raymer and I'm looking forward to guiding you through the virtual jungle which is Webpack and JavaScript modules. In the first place, I will be talking to you about JavaScript modules because knowing something about JavaScript modules provides crucial backgrounding to anyone who is seeking to use Webpack with facility. There are two more tracks, this track 2 and a following track 3 in this initial set 1 for Webpack course training. These two tracks, along with the overview at track 1 you've already worked through with me, comprise the information I feel supplies to you with the basic prerequisites for you to go on and learn Webpack proper and properly. JavaScript module systems are intimidating to most developers, but understanding it is vital for modern web developers. The intimidation is felt by more than just new developers. Just as good thinkers divide their ideas into categories and subcategories, so do good programmers divide their programs into modules and functions. Modules can be compared to entries in an encyclopedia. Each entry coalesces around a particular topic. Good modules, like entries you would expect in an encyclopedia, are highly self-contained, having distinct topical practical use. This allows them to be shuffled, removed, and added as necessary without disordering the system overall. There are lots of benefits using modules in order to avoid a Frankensteinian amorphous code base, once referred to as spaghetti code. One of the chief of these benefits is maintainability. A well-designed module will lessen the complex interdependencies within the parts of the code base as much as possible, so that it can grow and improve more or less autonomously. Maintaining modules is much easier when modules are decoupled from one another's pieces of source code. Going back to the analogy of an encyclopedia, if you wanted to update an entry, it would be a nightmare for a small change to one entry to require you to tweak every other entry as well. Instead, you'd want the formatting and layout so arranged as to be able to make improvements under any and each topic without other topic entries. Another benefit to opting for modular design is the ability to use namespacing. Note, namespacing comprises a set of symbols which are used to organize objects of various kinds so that these objects may be referred to each by name. Namespacing is beneficial because JavaScript demands that variables outside the scope of a top-level function are global. Note, scope determines the accessibility, visibility of these variables, but only within the program. Variables defined inside a function are not accessible, visible from outside the function. Because of this, it's common to suffer namespace pollution, where completely unrelated code are sharing clusters of global variable names. Sharing global variable names between unrelated clusters of code is bad development practice, since doing so allows a situation in which unrelated functions may be depending on the same variable or method name. Modules allow us to avoid this namespace pollution by creating a private space in which to park our variables. Another benefit of modular practice is reusability of code. Fact, developers do reuse their code from old projects, recycling it into new projects as they see appropriate. But let's take this example. Suppose you find copied to your current project some utility methods you wrote from a previous project. Problem: if you find a better way to write some part of that recycled code, you'd have to go back and remember to update it everywhere else in the project where you'd recycled it. So, being modular, using modules, helps you more easily keep track of the code and thus allows you to recycle the code without anxieties. There are many ways to incorporate modules into your programs. Let's walk through a few of them. Note, the module development pattern is classified as a JavaScript development pattern. JavaScript natively doesn't support the class keyword, but the module pattern can be used to mimic in your project the concept of a class. Note, in object-oriented programming, a class function is an extensible program code template for creating objects. Classes provide initial values for state, member variables, and for implementations of behavior using member methods. This mimicry simulates pseudo-public and private methods and variables inside a single object, in a similar way to how classes are created in other programming languages like C# or Python. This simulation allows us to create a public-facing API, an application programming interface, so as to be able to expose to the world those methods we choose to. At the same time, the module pattern allows the encapsulation of private variables and methods within a closure scope. This may sound trivial, but without some sort of encapsulation, it is a matter of time before two modules conflict with each other. Encapsulation is essential to prevent conflicts and ease development. There are several ways we can accomplish the module pattern. In this first upcoming example, we'll be using an anonymous closure. By putting all our code in an anonymous function that will help us accomplish our goal. Note, an anonymous function is a function which has been declared without any named identifier to refer to it. As such, an anonymous function usually is not accessible to the developer to reference after its initial creation. Remember, in JavaScript, functions are the only way to create new scope. Look at this piece of code. This function prints out the string, "Hello World." By us having used this construct, our anonymous function has its own evaluation environment, also known as its closure, and upon closure, we can immediately evaluate it. Note, a closure comprises a combination of a function bundled together, enclosed, with references to its lexical environment, the surrounding state. In other words, a closure allows us access from within an inner function to an outer function scope. In JavaScript, closures are created every time a function is created, and always at function creation time. To use a closure, define a function inside another function and expose it. Exposing a function is to return it or pass it to another function. The inner function, having been exposed, will have access to the variables in the outer function scope, even after the outer function has returned. This procedure then lets us hide variables from the parent global namespace. And this hiding provides for a distinction between public and private. By using this approach, you can also use local variables inside this function without risking accidentally overwriting existing global variables. The first console log output "Hello World," while the second console log outputs "Hello, I'm a global variable," smiley face. Note, the closure nonetheless still has access to the global variables. Note that the parentheses around the anonymous function are required. This is because statements that begin with the keyword function are always considered to be function declarations. Consequently, by us using surrounding parentheses, we avoid any declarations and create a function expression instead. Another approach to modules used by libraries like jQuery is the global import. A global import is similar to an anonymous closure, except now we pass in globals as parameters. Take a look at this code. In this example, global variable is the only variable that's global. The benefit of this global import approach over anonymous enclosures is that you declare the global variables up front, thus making variables emphatically visible to developers working with the code. Another approach used by developers is to create modules by using a self-contained object interface, like so. This approach lets us decide what variables or methods we want to keep private, for example, my hello, and what variables and methods we want to expose by putting them in the return statement. This approach is very similar to the global import approach, except that this way you ensure all methods and variables are kept private until you explicitly choose to expose them. Note, the syntax of all these approaches are often described as IIFEs or IFEs, immediately invoked function expressions. The approaches we have looked at all have one thing in common. This is a use of a single parameter global variable to wrap the code in a function, thereby creating a private namespace for the global variable by having used a closure scope. While each approach is effective in its own way, each has its own particular downside. Let's examine the downsides of these approaches one by one. Let's assume we have two such modules, A and B. B must have A to operate, but A does not depend on B. Let's also assume that, for sake of good practice, A and B are in separate files. For one, as a developer, you'll need to be aware of the right dependency order and to remember, load your files strictly in that order. As a developer who is managing dependencies, getting these vital things right gets harder the larger your software becomes. Another downside is that any of these modular approaches can still lead to namespace collisions. What, for instance, if two of your modules get named the same name? Or what if you have two versions of a module and you find you are needing both? Can we design a way to ask for a module's interface without going through the global scope? And that's what we'll be answering in our next lesson, Other Module Systems. In our next lesson, we'll be introducing and discussing CommonJS and asynchronous module definition. I'd like to welcome you all to this next lesson of Set 1 of the course on Webpack, sponsored by EduOnix. My name is Matthew Raymer, and I'm looking forward to guiding you through the virtual jungle, which is JavaScript modules. In our previous lesson, we covered IFEs, immediately invoked function expressions, as a way of addressing JavaScript modules. In this current lesson, we'll be answering the question, can we design a way to ask for a module's interface without going through the global scope? CJS, CommonJS modules are one method to deal with these problem situations. A CJS, CommonJS module is essentially a reusable piece of JavaScript which exports specific objects, making them available for other modules to be able to requisition for in their program. Note, CJS is a volunteer working group and it designs and implements JavaScript APIs in the case of declaring modules. Node.js frequently uses this volunteer working group format for modules. For CJS, each JavaScript file stores modules in its own unique module context, just as if it were wrapping it in a closure. In this scope, we use the module exports object to expose modules, and we use require to import them. When you're defining a CJS module, it might look to you something like this. We use the special object module and place a reference of our function into the property module exports. This lets the CJS module system know what we want to expose so that other files are able to consume it. Then, when a developer wants to use my module, she can require it in their file like so. There are a few obvious benefits to using CJS over the module patterns we discussed beforehand. These are the benefits that it avoids global namespace pollution by making our dependencies explicit and provides a very compact syntax. Note, CJS takes a server-first approach and synchronously loads modules. CJS using synchronous loading matters because if we have 3 other modules we need to load, CJS will load them one by one. Synchronous loading doesn't damage performance on the server, but it does hurt application performance when you're working with JavaScript in a web browser. This performance difference arises because reading a module from the web takes considerably longer than reading from a disk. Remember, for as long as the script that loads a module is running, it blocks the browser from running anything else until the script is finished loading. This strange behavior arises because the JavaScript thread stops until the code has been loaded. So much for CJS. What if you want to load modules asynchronously? What we'd need is called asynchronous module definition, or AMD for short. Loading modules asynchronously using AMD looks something like this. What's happening here is that the define function is taking as its first argument the complete array of the module's dependencies. These dependencies are loaded in the background in a non-blocking manner, and once all loaded, they define a call to the callback function given. Note, in general, a callback is a function that is executed once another function has come back from being called, that is, has been executed, hence the name callback. In general, callbacks may serve any prescribed purpose, but in our case with AMD, the callback is serving to dominate the environment in which a module may be used. Next, the callback function takes as arguments the dependencies that were loaded. In our case, my module and my other module, allowing the callback function to use these dependencies. Finally, the dependencies themselves must also be defined using the define keyword. For example, my module might look like this. So we see that, unlike CJS, AMD takes a browser-first approach alongside asynchronous behavior to get the job done. Note, there are a lot of people who strongly believe that in a browser it just isn't favorable to go dynamically loading files piecemeal as you start to run code. I suspect this disfavor is due to the need for orderly loading so as to avoid omissions of definitions occurring. I suspect it also concerns dependencies having not been loaded so as to properly relate to one another. Aside from asynchronicity of loading, another benefit of AMD is that your modules can be objects, functions, constructors, and strings. Even JSON as well as many other types of module can load, but CJS supports only objects as modules. Note, AMD isn't compatible with I/O file system nor with any other server-oriented features available via CJS. Also with AMD, the function wrapping syntax is a bit more verbose compared to CJS's simple require statement. For projects that require you to support both AMD and CJS features, there's yet another format available, Universal Module Definition, or UMD. UMD essentially creates a way to support either of the two sets of features, whilst also supporting the global variable definition. As a result, UMD modules are capable of working on both client and server. Here's a quick taste of how UMD goes about its business. As you probably noticed, none of the modules in the example were native to JavaScript. I should note for clarity here that JavaScript supports only its own native modules, which is why we are and why we have to be simulating our modules here and using them with JavaScript. Instead, we've created ways to emulate a module system by using either the module pattern, CJS, or AMD. TC39, which is the standards body that defines the syntax and semantics of ECMAScript, has lately introduced built-in modules with ECMAScript 6, or ES6. ES6 modules, relative to CJS or AMD, manage to offer the best of both worlds, compact and declarative syntax and asynchronous loading. Note, declarative programming is when you write your code in such a way that it describes what you want to do, and not how you want to do it. It is left up to the compiler to figure out the how. Here's an example. In this example, 2 copies of the module are made from the counter original, the first when we export it and another when we require it. Moreover, the copy of the module available in the main.js file is now disconnected from the original module. That's why even were we to increment a counter, it would still return the value of 1. The counter returns 1 because the counter variable that we imported is a disconnected copy of the counter variable come from the module. So, incrementing the counter will increment it in the module, but this won't increment your copied version. The only way to modify the copied version of the counter variable is to do so at the place wherein the copy has been put. You cannot modify via the original module object nor where this original is situated. ES6 creates a live read-only view of the modules we import. These live read-only views allow you to split your modules into smaller pieces without losing functionality.
Thank you for watching. Don't forget to subscribe to the channel. If you like the video, do give us a thumbs up and share it. Also check out amazing discounts and offers on our premium courses in the description below.